for the people who came to my, to my aid. I feel a bit stupid. I'm sorry about that, all the, the problems that I have caused. I do hope that you will like the presentation. So this piece of research, well, let's start from the beginning. I have a BSc in mathematics, an MSc in intelligent systems, and a PhD in artificial neural networks and artificial vision. I have been at NCSR Democritos, which is a research institute in Athens, which also hosts the only experimental nuclear reactor, not only in Greece, but in the Balkans. So we had many visitors at the reactor doing experiments and research. And then in 2004, I decided that I wanted to, even though I was extremely happy there, I decided that I would like to be able to also supervise PhDs. So after a number of efforts, I was accepted at the University of Piraeus, where I am until today. The only bad thing being that I have not supervised anyone so far. But it's a nice job to be with students and to be able to help them and guide them. And I have also been a visiting researcher at Chalmers for a number of years. So that's it basically about me. Now. How can I go to the next? No, I went to the next one. Okay, whatever. So my interests are in artificial and computational intelligence, brain function, psychophysics, as well as signal processing, prediction, classification, and monitoring. Okay, so now I will discuss something that's quite different from the topics that have been discussed so far. This is a piece of research that was implemented by an MSc student, Nikolaos Moustakas, who's now in Germany and is really doing well. And Dimitris Karalekas, a colleague of mine, a mechanical engineer who helped us on the mechanical side of this research. Okay, so two publications came out of this piece of research. One was at an IEEE symposium, and the other was at the Journal of Industrial Ecology. Okay, so the problem can be expressed as follows. We would like to determine the properties of a maximally sustainable material for a given application, or if there are more than one material, that's even better. We start from known properties of existing candidate materials, and we actually create a correlation surface between material properties as input and environmental impact values as output of a number of known candidate materials. So we have the information both on the properties and on the impact values for all of these materials. Then we create a correlation surface and we identify the minimum of this surface so as to expose the properties of the maximally sustainable material. And this we will go through together in the next half hour. So we will demonstrate the material selection, and the application will be maximal sustainable liquid containers. of inert fluids. We'll see about that. And we will compare with classic interpolation and prediction techniques. And finally, we will see, you will see the results of a multi-criteria and a sensitivity analysis to confirm stability of the specific material to the problem at hand. So this application can be used in practice. So what I will show is a simple problem, a problem that's used for demonstration of the methodology and of the algorithm and results, actually. So we picked up 10 polymeric materials, which are considered as materials that are suitable for manufacturing liquid containers complying to the usage profile. We don't want anyone to get poisoned by these containers that we are going to create, and so on and so on. So there was a number of materials that could be used, you know, for this profile. You can see them here. They have to do with polyethylene, polymethyl, polyamide, polycarbonate. So it was all kinds of materials that were more or less, some of them more and some of them less, but all of them could be used for the application at hand. So what we wanted was to propose some solutions using our methodology and have the engineers come back to us and say, you know, this is a good idea and this isn't a good idea, and take it on from there and make our prediction, let's say, tool even stronger. So perhaps we can have exclusively plastic, we said, rather than Tetra Pak containers. So this was an idea. And of course, there were some things that we didn't want. We didn't want permeability to light, and we didn't want something that couldn't be a material that could not be recycled. We had other constraints as well, but these are the main ones. Okay, so I will go through some of them. So PE, which is the most common plastic, and it's used for packaging, you know, mainly plastic. Most of the plastic bags and films and containers or bottles are made of PE. Then there's PEN, which is very well suited to bottling beverages, but is susceptible to oxidation. So this would not do for beer. Then there's PET, polyester, which is very versatile. It is used in synthetic fibers and has excellent barrier qualities. So it's ideal for beverages, for food, for liquids, for soft drinks, and so on. Now, okay, so PET can be sandwiched because many times you have different layers, one on top of the other, to make the bottle or the container. So it's easy to be sandwiched with other materials that are good for food and liquid packaging. And they're also used for thermal insulation, which might be a good thing with bottles. Okay, and so there are some properties there. I think the one that we're mostly interested in, I just mentioned. Also, they can be, this material PET can be frozen, okay, and nothing goes wrong. But when filled with glass particles or fibers, it becomes stiffer, which again is not a bad thing because it becomes also not more durable, but it depends on the feel that you want to, the bottle, you know, that you use for your liquid to have, because this is a multi-criteria problem which must be solved so that not only the manufacturers and the sellers of the product are happy with, but the consumers are also happy with. Now, PET can be subjected to various types of degradations. And you can see this, it can be discolored, it can be reduced in molecular weight. There's the formation of acetyl. So this is another problem, along with poor processability and performance. Phthalates, which is not necessarily a good thing, are used to make PET more durable and transparent, but as you can see, the amount, the limit can be exceeded for a number of water or soft drink products. So this is why the limit, it's after a year of storage at room temperature. Otherwise, we have liquid infiltration. So part of the PET will go to the liquid. Now, there's also PMMA, which is a transparent thermoplastic material, often used as a lightweight, shatter-resistant alternative to glass. It's economic, and it's an economical alternative to PC with extreme strength. When extreme strength is not necessary, as happens for our bottles, and it doesn't contain harmful elements as PC does. And it's easy at handling and processing, so that would be good for the customers. But it's brittle when loaded, so one cannot load one tray of filled bottles over the other, okay? Especially under an impact force, something that falls on the tray. Now, there's PS as well, which is clear, hard, but brittle, but also very inexpensive. It's not a good barrier to oxygen and water vapor, and it has a relatively low melting point. Of course, it doesn't matter for the containing liquid, but it might matter if these trays, let's say, of of bottles were left in the sun, especially in Greece, and hot areas. It is used for protective packaging. It's CD and DVD cases, basically. Also peanuts, and it's used for containers, lids, bottles, trays, and so on and so on. PVC is the third most widely used plastic after PE and PP. It is white, brittle, which is not good, but insoluble in alcohol, which is very good. And when used, it can be made softer, more transparent, and more flexible by the addition of phthalates. It can also be used in clothing, upholstery, electrical cable insulation, and in many applications for replacing rubber, which is a bit of a strange thing. Okay. PP, which is a thermoplastic polymer used in packaging, ropes, thermal underwear, and carpets, plastic parts, stationery, and you can see the polymer banknotes, which might be of interest. It's rugged and unusually resistant to chemical solvents. So this is a plus, bases and acids as well. And now we have the UHMAW HDPE, which is very good at holding load. So we can stack trays one over the other. It's very tough, and it has the highest impact strength, we'll see about that, of all other thermoplastic material. It's odorless, tasteless, non-toxic, which is also very good, and highly resistant to corrosive chemicals, except oxidizing acids. It has very low moisture absorption and a very low coefficient of friction. Okay, self-lubricated and highly resistant to abrasion. So times for in some forms 15 times more resistant to abrasion than carbon steel. So you see there is a wide variety of materials with different diverging, let's say, qualities, and the problem is to actually try and find what would be the best one to use. Okay. Oh,
Hello, Tatiana.
Hello.
Is this okay for you?
Yeah, it's okay.
Okay, so thank you for this wonderful presentation, full of very interesting information.
So I'm sorry. Yes. Can we go to let's say the last 2 slides or 3 slides so that I can show the technique, because I haven't shown anything yet.
Yeah. Go ahead. Go ahead.
Yeah. Okay.
This one?
So what we did was no, this we have seen, I think. Okay. It's just the procedure that I wanted to show, because all of this is very interesting, but perhaps not to the uninitiated. Okay, now it. So what happened was we, so following the elements that could be used, we selected 5 mechanical properties: Young's modulus, compressive strength, yield strength, tensile strength, and fatigue strength. And in the following slides, you can see, well, I don't know. I mean, I'm really sorry about that. It's just such a shame, because I was very well prepared, but for anyway, these things happen. So yeah, if we have to finish here, we can finish here. I would just hope that, you know, the organizers could send the presentation to the participants, so that if there is there are any questions or any, you know, ideas of collaboration, we could discuss this. I mean, I would be grateful if this could happen.
Okay. Thank you so much. So
I'm really sorry.
No problem. I think it was pretty much clear, and we've received a file in the discussion, but unfortunately, we cannot download it. I'm talking about myself. I cannot download it. If you can send it once more, NNN, please. And otherwise, I don't know if the other participants, if you have some questions to Tatiana, don't hesitate, please, to activate your microphone and ask your questions.
I think the questions will come once they have seen the entire presentation.
Maybe, yeah.
Yes, at least it would be useful for us to understand what is the bottom line. Which kind of procedure did you try to apply for selecting the best material?
I applied PNNs, probabilistic, general regression neural networks, which is a very simple kind of network, but which was very good at simulating the, let's say, hypersurface that goes through all of these materials, so as to have an idea of how we have an idea, by going to, let's say, the lowest points of this hypersurface, you can find the exact absolute best material given the properties that we want. So this can be applied everywhere. And what we also did was we had, wait, now it goes fine. Before it didn't want to. There was a GA, a genetic algorithm, a very simple one actually, which found the optimal point in the hypersurface, which we projected back, and we found the characteristics of the maximally sustainable material for our investigation. So we found a new material. I don't know, maybe you can see it on screen, which is of lower environmental impact than all the materials that were used. And it's quite close to the mechanical properties of PVC. And I have the values here, and I can it shows here that it's not just a perturbation of genes, but it's a novel, in terms of mechanical characteristics, material. Okay, so and in this, material scientists and design engineers can also take ideas from what we have done, and they can also give us information so as to make this more complex and more applicable to, you know, the real world, rather than having something that is a pilot thing. And we also did a multi-criteria analysis. So we saw what the necessary decrease in an environmental property should be in order to produce something that's more sustainable than what we have at the moment. We tried changing one property, leaving the others alone, which was the fair thing to do. The sensitivity analysis shows us that PVC is really the best, let's say, from the existing materials that we use for these purposes. Then there's PET, and HDPE is very, very small. Of course, the others do not really count. It's very small, their participation in this. So I would urge you to read the paper. If anyone would like to read the paper, please email me and I will send it to you immediately. Or you can find it, of course, on the web. So I'm really sorry for